good afternoon, class. This is Professor Harn. Today is November the 7th on Tuesday, and this will be a video lecture due to the fact that I'm out of town. So as a reminder, our homework 6 is due on Tuesday the 14th, so 1 week from today, and that will be due in class. And today, so moving beyond that preliminary, today what we'll do is cover some common examples problems in room acoustics involving transmission loss, which is what topic that we had covered last time in class on the 2nd of November. Example problems in room acoustics involving transmission loss. Now remember that transmission loss is computed as 10 log 10, 1 on the transmission coefficient, where tau is the transmission coefficient, which is the ratio of transmitted to incident powers, where tau is ratio of transmitted. These capital Pi's are, of course, the sound powers. So, transmitted incident powers. Due to the expression here in the logarithm, we can alternatively write this transmission loss as negative 10 log 10 tau. And we will use both notations here towards the problems that we'll look at today. So very often, as a first case example, we don't exactly have transmission problems between rooms or spaces that involve only a single wall divider. Very often the wall or span between two rooms will be composite. So one example would be you're inside your apartment, and this could be, for instance, the wall that faces outside. So for instance, you may have that front door, and then a large front-facing window. So in this case, to determine the total the effective or composite transmission coefficient, and then out of all of these, we have this is incident and transmitted power. Considering this composite surface here, or composite wall, the effective or composite transmission coefficient is then a surface area weighted sum of the individual transmission coefficients. So this is the total surface area, and this is the surface area and transmission coefficient of the ith area. So let's consider this. Let's consider a specific example where we will have that front door, front-facing wall with a door and a window. And let's say that our overall span of that wall is 7 meters and height is 4 meters. And let's say that this door is a pretty standard size of about 1 meter in width and 2.7 meter height. And that this window covers 3.5 meters in width and 2 meters in height. Now, in terms of building materials, let's consider that we have a single pane glass of 8 millimeter thickness. We'll consider that this door is a standard door in mounting. While the wall itself is a single leaf of brick of 125 millimeter thick. It's a standard moderate thickness brick. So let's find the TL of this composite wall. So to do that, we'll need the TI of each surface. So to that end, we will also require the TL values of each of these surfaces. So what we can do is turn to tables. So first, turn to tables that report TL values for measured materials. Including construction materials. So there is one of these tables in the back of our notes. So if I turn over here to course notes and go to the back of this document, I'm not sure if that's shown in the table of contents, but this final table, which shows up after all the notes properly speaking, gives, as cited here, airborne sound transmission loss values for common building structures and materials. So these are ordered in terms of what they are, their thickness, their surface density or weight. So that means, as a first example, the 1.5 millimeter lead sheet is a thickness of 1.5 millimeters, which would give, based on its volumetric density, a weight of so much kilogram per meter squared. And then the TL value is reported for select octave bands. So let's do a problem here in the octave bands of 250 hertz 500 hertz, and 1000 hertz. So let's then write out the transmission loss for these materials. So we need to find specifically single pane glass, 8mm thick. We need standard door, and the single leaf brick of 125mm thick. And what we'll do is write out our TL value, and then we'll need to compute the corresponding transmission coefficient for that contribution. So we'll have TL and tau, 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 TL, tau, TL, tau, TL, tau. I'm going to preserve some other space over here for something else momentarily. But we need to find the TL values for these 3 octabands in our table. So let me bring this over, and I'll keep on the screen some of the names they're showing. We want single pane glass of 8mm thickness. So I happen to know that the single glazed windows are down here, so single glass and heavy frame, 6mm thickness. There we go, 8mm thickness. So the order of the columns starts in the 63 to 125. So the columns over here that would be 3rd, 4th, and 5th are the ones we're looking for. So 8mm, 1, 2, 3, 4, 5. So these 3 values we will put into our notes there. So we have 25, 31, and 32. All right, now let's look for the standard door. I happen to know the doors are further down. So this is a pretty standard door. Normal cracks is usually hung. And so we want the 3rd, 4th, and 5th values, 13, 14, and 16. And finally, brick of 125mm thickness. So there we go, single leaf brick, 125mm thickness, 3rd, 4th, 5th, 3rd, 4th, 5th, 37, 40, and 46. Now the transmission coefficient, recall, is associated with the TL from this equation. So then we can turn to our handy-dandy MATLAB and compute, for instance, what the transmission coefficient is in these cases. So let's consider the first example. That would mean I have to actually move my notes because it's over my keyboard. So we have 25. I'm going to do this. I can get that on the screen. So now actually I can access my keyboard while typing here. So we have 10 to the negative 25 divided by 10 Alright, so what we'll put in here for the transmission coefficient will be 0.00316. And let's keep going. And to speed up, I will just write out all of what these are that I have pre-computed for saving time. There you go. And these are all of our transmission coefficients that correspond to the ith surface in the specific octave bands that we'll look at. So the other thing that we need to compute the overall transmission loss of this composite surface are the composite surface areas. So this last column will be our S sub I in meters squared. And looking back to our problem, we had surfaces of 2.7 meters squared for the door, for the window we have 3.5 times 2. Let me get this back out of the way, sorry. We had 3.5 times 2, that's 7 meters squared for the, I'm sorry, not for the door, but for the window. And then the difference from 7 times 4, the overall, minus the door and the window, you ran that number, you'd get 18.3. So then, to find the TL of composite wall, we need to compute the transmission coefficient from that composite expression. And then ultimately, thereafter, that transmission loss. So let's make then a new table where we will work out these values. So using our values from above, what we will do is that for the 250 Hertz octave band, for the 500 Hertz octave band, and for the 1000 Hertz octave band. Here, then we'll compute the transmission coefficient. We'll find that this, once we run our computation here for our numbers given above, along with these surface areas, will lead to composite transmission coefficient in the 250 Hertz octave band of 0.00575, in the 500 Hertz octave band 0.00410, and for the 1000 Hertz octave band 0.00259, leading the transmission loss values in dB of 22.4, 23.9, and 25.9. So let's look at these values with respect to what's making up these contributions. So clearly, RTL's transmission losses are in the range of just 20 plus decibels. When you compare that to the brick that makes up a significant proportion of the overall surface area, these values in the low to mid-20s are much less than the values associated with the brick itself, even though, again, it's predominating the overall surface area. Instead, these values are apparently much more weighted towards the door. The single pane glass, except for this lower value, it's much greater, almost 6 decibels greater in this case. So it looks like the weakest link, the door, it even occupies a smaller overall surface area. So we could conclude here that from this example, we find that the transmission loss is strongly influenced by the weakest link, so to speak, or I'll say links in a composite wall. This example is exacerbated if we consider cracks. So what if the window is open by 10 centimeters, which is around 4 inches? So what happens to these TL values? So now, SI, the surface area of the window, will change, and you have to think about if the windows are open, and let's presume that the windows are open in a pretty conventional way such that they open up. So here we now have 10 centimeters. We still have a height of 2 meters and a width of 3.5 meters. So now the SI of the window is 3.5, 1.9 meters squared, where the SI of the opening is 3.5, 0.1 meters squared. Now, we then have to find, okay, so if this open area is contributing, it's just straight outdoors, so to speak, or whatever is on the other side of that window, we need to find what that transmission coefficient is of the opening. So at all frequencies, the transmission coefficient of opening is what? It's 1. Because energy, acoustic energy, flows without impedance. Or flows without resistance, rather. Sorry. Not trying to mix terms. So if we then recompute our composite tau and TL, what will we find? So what are these values? I bet you can do them before I can. So we'll find that our tau is 0.0182 in the 250 Hz band, in the 500 0.0166, and in the 1000 0.0151, which lead to transmission loss values in decibels of 17.4 dB in the 250 Hz octave band, 17.8 in the 500, and 18.0 in the 1000 Hz octave band. So how does this compare to our prior values? Before our TL was, or were, the values were 22.4, 23.9, and 25.9. So that opening has passed a tremendous amount of energy, even though it only constitutes a small area of 0.35 meters squared. So our weaker link, which previously was the door, has now been made weaker by this small opening. So once again, we see an emphasis on the significance of these weak links. So clearly, the transmission loss is strongly influenced by the weakest links. Previously, it was the door. Sorry, I'm looking for my sketch. Previously, it was the door, and now it is the crack under a window, the opening of a window. So the doors and cracks under a door are notorious for this type of concern. The doors are notorious to lead to cracks or openings that freely pass acoustic energy. And this is either due to poor design, poor building construction, so this could be, for example, the door frame is too large. These 2x4s are not cut necessarily that form the frame of the door They're not necessarily cut with exacting tolerances. Or it could be poor installation of the door, because the hinges have to go on at the right location, otherwise a crack at the bottom will form. And these are all done by people, and people are imperfect, so there's many possibilities for error. So let's consider this other example. Where we have a common 7-foot by 3-foot door so the transmission loss in the 500 hertz octave band is 29 decibels. So if a 1/2 inch crack is introduced in addition to door area, what will be the total or composite TL? Can you solve that? So let's do it. The transmission coefficient of the door in that 500 hertz octave band will be 10 to the negative 29 on 10, which is 0.001259. Where, as the door, the transmission coefficient of the crack is 1. So that the composite transmission coefficient, if we write this out, will be, even using feet, 7 times 3 is the area of the door, and the transmission coefficient of that is 0.001259. Now the crack underneath the door will have that 3-foot width. So we'll have 3 foot times the height of the crack. Now it's a 1/2 inch, but putting this into feet is 1/24 of a foot. Transmission coefficient is 1. So that's in the numerator. The overall area is in the denominator. So we have 7 feet in one direction and 1/24 added to that, and they both share a 3-foot height, or width rather, and that composite transmission coefficient is 0.007169. So this leads to a transmission loss of minus 10 log 10 tau, which is 21.4 decibels. So, due to the crack, TL went from 29 to 21.4. Significant reduction that's very easy to detect. So a very large drop in excess of 6 decibels there, 7 decibels there. once again, the weak links, and in this case, ineffective fabrication, very likely, or installation, can lead to a very significant reduction of the transmission loss. Great. So let's consider another example. It's fairly common for design purposes. So let's consider a schematic that was shown previously in class. We have a source that leads to an SPL1 in some source room that has a shared wall to a second room where the SPL is denoted SPL2. So in class on the 2nd of November, we had a relationship that said the SPL2 was equal to the source power level, L sub power, capital Pi, plus 10 log 10 for on the room constant of the source room, plus 10 log 10 of the shared wall area times the inverse of the room constant of the receiving room, which would be written as 1 on A bar R on SR, A bar R, and then minus the TL, the transmission loss. So let me remind you of those terms. So R is the room constant of source room, so that R is equal to S A bar on 1 minus A bar, the average absorptivity of the source room. And this term over here, we could express R sub R as the room constant of receiving room so that R sub R is equal to S sub R, A bar R on 1 minus A bar R. So we see that over here as well. So the question is, if we have the following, we have an old room constant of the source room is 0.2. I'm sorry, if the absorptivity of the source room old is 0.2, if the receiving room old absorptivity mean is 0.2 as well, and the transmission coefficient of the shared wall is 0.002, let's ask, what is more influential? To change SPL2. Is it a 10% increase from A bar old? Is it a 10% increase from a R bar old? Or is it a 10% reduction of the transmission coefficient of the shared wall. So can you solve this? What is more influential to change the SPL2? Where we have that equation written above. So let's say we can't do anything about the source power in the receiving room. So the source room. Let's say we can't do anything about the source. If we can address the room constant that's associated with this old source mean absorptivity of the source room, or if we can address the mean absorptivity in the receiving room, it was originally this value, or if we can address the transmission coefficient that's associated with the shared wall. What is more influential? Which of these changes? Can you solve that? Okay, let's solve this. So let's write out a few things that will help us. Let's write out the delta decibel of SPL2 associated with change of the room constant of the source room. So let's write delta dB is equal to 10 log 10 4 on the room constant of the source room new minus 10 log 10 the original. So that would be 4 on R old. So R new, if we have this 10% increase from A old, that can be written as S, which will not change, 1.1 A bar old divided by 1 minus 1.1 A bar old. Whereas R old is S times A bar old and 1 minus A bar old. Now note that we can simplify this delta dB using just these values, because due to the logarithm here, we could also write 10 log 10 R old on R new. So if we take this expression here, we could do R old on R new, and what would we get? Well, after simplification, we'd have 1 minus 1.1 A bar old in the numerator, and in the denominator, we would have 1.1 and 1 minus A bar old. So what's our 10 log 10 of this, given our interest to find the delta dB? Well, when we do this, we'll find the delta dB for source room is negative 0.52 decibels. So increasing the mean absorptivity of the source room by 10% will decrease the SPL2 by 1/2 a decibel. Now let's think about the math that we just followed. A delta dB, R new minus R old being equal to this ratio. Think that if we consider our SPL2 expression, a 10% increase from the mean absorptivity in the receiving room from the old value, we're looking at this a similar form of expression here. The only thing is that we have an S sub W for the shared wall in this expression. But if we're looking at the delta dB, we can see that the SW would show up in both terms. So the same difference, same delta dB value would be found according to 10% increase in a R old, A bar R old. So it doesn't matter whether that 10% increase occurs for the source room or for the receiving room. We have the same delta dB that would be realized, a minus 1/2 decibel change. So then we need to find out what is the delta dB associated with the change of transmission coefficient. So we can do that fairly easily. Let me move this away. We can say delta dB will be the transmission loss new minus transmission loss old which we can write as minus 10 log 10 of a change in the transmission coefficient. So recall that we have a consideration of a 10% reduction in the T old. So our new will be 0.9 tau old. So, and it's minus T old, so these minuses will cancel, so that will be plus 10 log 10 of tau old. So due to the logarithms, this is easy enough to express as 10 log 10 tau old divided by 0.9 tau old, which is just 10 log 10 on 0.9. And we can run that number quite easily and find that the delta dB by 10% reduction in tau old is 0. Actually, let me make a correction here. I realize I've written this incorrectly. The TL shows up in our equation of SPL2 already with a negative sign. So to compute the difference, it would be minus TL new minus TL old. So plus, which would give, actually all of this we can just put a negative sign in front of. So we could do negative that, negative that, that, which would lead to, apologies for that, a delta dB of minus 0.46 decibels. So what we conclude is that whether using a 10% increase in the mean absorptivity of the receiving room or of the source room will achieve very slightly greater decrease in the SPL2 in that receiving room than we would by reducing the transmitted acoustic power by 10%. So we may say, is this conclusion dependent upon these values? Well, let's try some different values. Let's come to our expression here of looking at the delta dV, where we had this 10 log 10 ratio. And I'm going to bring MATLAB up to the screen here to help us out. So let's do 10 log 10 1 minus 1.1 times A old divided by 1.1 divided by 1.1 divided by 1 minus A old. There is our negative 0.52. So let's make A old 0.5. So that value grows. As the mean absorptivity approaches 1, in other words, those walls in the source and receiving rooms are perfectly absorptive, it approaches a certain value. Let me get that onto the screen. Well, at some point it grows to a point that it becomes complex, but it approaches somewhere around 10 decibels before that occurs. So let's consider the other case. What if the source and receiving rooms were very reflective and our values decrease? So now we're at a 2% absorption, mean absorptivity. Or what if we go to 0.2%? Now you might say, if we're changing that mean absorptivity by 10%, why is the delta decibel change approaching a constant value? What if we keep going to the point where there is no difference? Why do we keep finding a change in decibel? Well, let's look at this expression that we have here on our paper. The room constant, so in other words, why do we find a finite delta dB for change, percentage change in A bar, even when A bar goes to 0? Reflective source and or receiver rooms. Well, the room constant is the area times the mean absorptivity divided by 1 minus the mean absorptivity. So when a bar is much less than 1 and approaches 0, R is approximately S times A bar. So that a percentage change in A bar is equivalent to a percentage change in the surface area. So in other words, the reason we have a finite decibel difference for that percentage change in the mean absorptivity, even when that mean absorptivity goes to 0, is because it's functionally equivalent to a percentage change in the area, meaning that less acoustic energy ultimately arrives at the shared wall, because either the source room or the receiving room is larger. Thus, the diffuse field acoustic energy density will reduce by the same delta D B amount. So, these examples that we covered today are fairly representative of studies, or rather of problems that we may encounter when it comes to the use of transmission loss and room acoustics. So we'll end with that today and pick up on Thursday on some further studies of transmission loss through partitions. Have a good day.